So in this tutorial, I will show how to train neural network for the prediction of material properties. So neural networks are computational system inspired by biological neural network, which we will use for the prediction of for material properties. In this case, this is a picture of a biological neuron. Neural network have a multiple input and make predictions by multiple outputs. So in this Google Drive folder, 2D NN, I'm showing these are the all neural network predictions for different material properties. I am here showing for 2D plasma frequency in x direction. After opening the Python file in the Google Colab, the name I'm setting the variable to 2D text, installing the composition based picture vector and importing this package. If you have already installed, you don't need to do this step in your local computer. So for the machine learning, I'm importing Keras. Keras is the machine learning library from Google, like PyTorch, which is another machine learning library from Facebook. You may remember in last tutorial we have used scikit-learn, which is machine learning library for classical machine learning models. For neural network, we are using Keras. Keras is imported from TensorFlow, which is also a machine learning library for machine learning from Google. So we're importing NumPy, Pandas, Matplotlib. Then sklearns, we are importing train test split and standard scalar and normalizing operators. From the Keras, we are using the sequential model with a dense layers. We are mounting the Google Drive in the path cloud content / drive. Then we are reading the our data from this path using this command. After, if you run, you will see the first 10 entries of this data. C2DB underscore 2D plasma frequency x direction. Then we will do the featureization. This is a necessary add-ons uh, for determining the accuracy of our predictions, like R-square value, mean absolute error, etc. Here we are defining our machine learning model in a for loop. It takes the different featureization scheme and put in this machine learning model and generate the featureization vector for all the elements in the array. So we are initializing the neural network with a random manner. We are using seed equal to 0 for reproducibility. You can read the comments for more knowledge. The model is sequential model. So the activation function we are using is rectified linear output ReLU. There are other activation functions like tanhx. This will reduce the output between the values 1 and 0. Here we are, first layer is 32 inputs, second layer is 64 input, and can include more layers to our neural network, deep neural network. So we can change the number of layers for better prediction or worse prediction. So it is, you have to try different times to find the best layers. The model and the output, we have one layer, which is the output we are using for the prediction. Optimization we are using is RMS propagation. mean squared propagation. Then we are putting epochs for 300. Is how many number of time we are passing our entire data through the machine learning model. So each of passing the model will learn. Too much higher value of epochs will be bad for the fitting or prediction. So we need a optimum value. I have here choose the 300. You may need to change the value according to your input. So this is the function to plot. This function we are using to plot the mean absolute error changing over each epoch. We are plotting using matplotlib. Here we are finding the model evaluation metrics using TensorFlow add-ons like a root to mean square error. We are finding R square using NumPy from the result we are obtaining from the predictions. So these are the plotting for like previous step, plotting for the predicted value and the actual values on the x-axis and predicted values on the y-axis. So this is the output of the last cell. We are using 2 layers with 34 neurons, with three layers with 32 neurons in the first layer, 64 in the second layer, and 1 in the last layer. So you can see in each epoch the mean absolute error is actually first decrease, then variable. We can do some fine tuning to improve the prediction maybe. So here Jarvis is the best featureization scheme. So we have find the best featureization scheme. Then using the best featureization scheme, we will we generate the features again. When we will split the data into training and testing set. We'll create the model again like previous step. This time we are not looking through all the featureization scheme, because we already know the best featureization scheme for the 2D plasma frequency acceleration data is Jarvis. So if we are training the model, the plot of mean absolute error over each both. This is the function joblib. We are importing joblib function to save the model into this path. Save model neural network nn underscore Jarvis name, which is 2D plasma frequency x joblib. So we don't need to retrain the model again. We can load the model and make the predictions. For testing the model evaluation metrics, we'll use this function, which will print the mean absolute error, which is, this case is 1.54. So this is how we make predictions using neural network. Just model.predict xtest.flatten. So these are the predictions. These are the real values and these are the predictions. 7.3, 7.9, 6.19, 5.42. We can plot these real values on x-axis and predicted values on y-axis. This is the function here imported TensorFlow add-ons to predict R-square value. In this case, we have an R-square value of 0.57. 1 is the maximum, so our prediction is about 57% accurate. So here we are plotting. Here the plot, the linear fitting is the orange line, and the dashed line is the ideal fitting, and these are the our predictions on the y-axis and real values on the x-axis. This is the performance of neural network I found after running the neural network algorithm on all these different material properties that I want to predict, and the best featureization scheme, Jarvis, one-shot, Matovec, all these, and the R-square values and mean absolute error. And these are the plots of the different properties we are predicting. Here you can see that the neural network was able to put all the predictions in like 1, 2, and 3, because as I said, this is a discontinuous values for the thermodynamic stability level. Still, neural network was able to predict more or less accurately without using any classification algorithms. The performance of neural network was not good, as the classical machine learning models after hyperparameter tuning or before hyperparameter tuning, because here I'm using C2DB database. Neural networks typically need a huge amount of data, and in the case of material science, the available data is less, so we expected neural networks to perform not good as classical model. We may do hyperparameter tuning on the neural network. This may increase the accuracy of prediction, but as I said, number of data points is less, so classical model perform better in our C2DB database.